I wanted to make a short video explaining the Pivot Lab from last week, just so that you know whether you were doing it correctly and what you were looking for. So I did it myself. I picked puck B, mass of 180 grams and a ramp angle of 5. The biggest thing that you needed to make sure that you did was line up the ruler right at the dry ice puck, and then to reset the clock so that if my clock is back here, my clock is negative. And then I start my time, and you can just reset your clock by hitting that button. And so the clock needs to be set to 0 at the time that this puck first begins to move. So I decided right there is where the string is cut, so I'm going to 0 it. Okay. So I started out just measuring my position and my time. I put the time first in even increments, and then the position second, because I like my independent variable to be first and my dependent variable to be second. You can ignore this column for now. All right, so this makes a nice position versus time graph. Notice how it's curved. That curved position versus time graph tells me that the velocity is changing over time. The puck travels a very small distance in the beginning, and then it gets bigger and bigger and bigger as time goes on, meaning it starts off with a small position versus time, or a small velocity, a small slope of this line, and then the slope gets bigger, or the velocity gets bigger. It covers more distance in the same amount of time. All right, the next thing that it asks you to do is to find the slope or the average velocity. If you pick 3 points to fit a straight line to, then the average velocity between those 3 points will be the instantaneous velocity at the middle point. So if I go ahead and curve fit this to be linear, I've already selected off these points, but notice how you can click points on or click them off so that you're not using those to fit. And so I have my 3 points here. My middle point is at 0.1 seconds. And my slope, or my A, that's the slope which is on your y equals ax plus b, my slope is 22.5 centimeters per second. This plus or minus is just the amount of error that's in that value. We can ignore that for now. So I will write that 22.5 as my velocity for 0.1 seconds. Boom. And then I just went through and clicked on and off these points and found the velocity at each 1/10 of a second through time. All right, so when I look at that, then when I look at my velocity versus time, I'm going to go ahead and turn off my curve fit. This line looks pretty darn straight. So when I say what's the proportionality between velocity and time are proportional. If you doubled one, the other one would double. If I were to curve fit this, I'm going to have to go ahead and click on some of my points. If I make a curve fit of this, I think that's all of the points. There we go. Then I end up with a slope of this line of 199 centimeters per second per second. That is a very weird unit. So about 200 centimeters per second. And what does that mean? Well, this is the change in velocity, the change in the rise, or the change in the y, over the change in time, or how the velocity changes with time. So 200, I'm just going to round it, 200 centimeters per second every second. This is what the velocity will increase by. So every second, my velocity will be going, or my car will be going 200 centimeters per second faster. So if it starts with 0 speed or 0 velocity, 1 second later, I'm going 200 centimeters per second. Another second later, I'm going 400 centimeters per second. Another second, I'm going 600 centimeters per second. So this unit tells me how my velocity changes with time. The rest of this was some questions to answer, talking about, what the units are and a little bit of other things. So make sure you come back into this. I think that I will have graded it and given you guys some information about that. But the right here is just what I said, that the slope tells us how much the velocity increases, and that this is a linear relationship, so the velocity changes the same amount of centimeters per second every second. I wanted to take this same pivot activity of how to find the velocity and do something that's a little bit different. So just a refresher, last time you did this, or when you did this, you found the position of the puck over time as it's sliding down the ramp, and graphed the time and the position, and it became curved. And then we graphed the velocity versus time, and that's a straight line. And so the velocity is proportional to the time. But we can do something that's a little bit funky in this, because this position versus time graph, because it's curved, we can say that the position goes as, or is proportional to, not the time, but the time squared. And we can find interesting information from our graph if we graph the position, not versus time, but versus time squared. So I'm going to go ahead and come back up to my data table, and I'm going to put in a new column right here. I'm going to insert a column to the right, and I'm just going to call this time squared. And that unit is going to be seconds squared, and the variable will be t squared. So everything's going to be squared. And so how am I going to find this? Well, we're just going to calculate it. So this format, this column is just going to be time to the squared. And we'll see if that works. All right, so if I squared 0.2, I would get 0.04. If I squared 0.3, I would get 0.09. So this is our time squared column. All right, what happens when we graph position versus time? It's curved. If we graph position versus time squared, this graph is linear. So the position goes as time squared, which that's sort of wild to think about. But if you look at the curve fit for this, we're just going to do a same linear curve fit that we've done before. Notice we have all of our points selected. This is giving me a slope of about 100 centimeters per second squared. Okay, so when I graph position versus time squared, I get a slope of 100 centimeters per second squared. Remember, when I graphed velocity versus time, I'm just going to do that again. Velocity versus time, not time squared, but time. When I graph velocity versus time, I get almost 200 centimeters per second, which is centimeters per second squared. So graphing the velocity versus time, I get the acceleration as my slope. When I graph the position versus time squared, my slope is half the acceleration that I got when I graph velocity versus time. Those units, centimeters per second squared, are the same units as you get, they're the same units, centimeters per second. I think that's so cool. We'll talk about why you see this, but so cool, so cool.